Forget rocky worlds like Earth and Mars. New discoveries about icy worlds like Europa and Enceladus make them the ideal candidates for the search for life in the universe. In fact, there could be hundreds or even thousands more worlds out there with the ability to support life. Of course, there's a problem. How do we search for life when it's hidden beneath kilometers of ice? Decades ago, Mars seemed like the most viable place to search for life in the solar system. The red planet is cold, dry, and airless today, but it certainly seemed to have liquid water there in the ancient past. Of course, wherever we find liquid water here on Earth, we find life at the bottom of the ocean, where crushing pressures would kill us in a moment, in steaming volcanic vents, beneath glaciers, deep underground, and even huddled in nuclear reactor cooling tanks. NASA's Mars exploration program has been following the story of water. Opportunity and Spirit discovered evidence that Mars had liquid water in the ancient past. And the Curiosity rover doubled down on that, finding minerals that indicate that there was water on the surface of Mars for a long time. But then, long ago, the conditions changed. Mars lost its atmosphere, became cold, dry, and inhospitable to life. It's possible that life could still be there on Mars, huddled underground in salty reserves that prevent the water from freezing or evaporating. But so far, scientists haven't found any of it yet. And this shows that life on rocky worlds is tenuous at best. Too close to the star, or not far enough, not thick enough atmosphere, or too thick, creates a world that's inhospitable to life. And even if a world was, briefly, a place worth calling home, main sequence stars are constantly putting out more radiation, shifting the habitable zone farther out. Think about how long Earth will be habitable. Life crawled out from the oceans 430 million years ago. And planetary scientists estimate that we've only got another 500 million to a billion years before the sun gets too hot and boils the oceans dry. But now we're discovering there are other places in the solar system to look for life, water worlds. In fact, the number of these places and the amount of liquid water on them is difficult to wrap your brain around. The Earth is a desert compared to the amount of liquid water that's out there in the solar system. Europa alone has 2 to 3 times as much water as Earth. And life there could be safe and sound, protected from radiation, meteor impacts, and nearby supernovae for billions of years, long after the sun has burned out and faded away. The first flyby of an icy ocean world came with the Pioneer missions to the outer planets. Pioneer 10 captured the first rudimentary images of Jupiter's Europa in 1973, but it wasn't close enough to make out any surface features. This was followed up by NASA's Voyager missions, which captured the moons of Jupiter in great detail: Io, Ganymede, Callisto, and especially Europa. By the time the Voyagers arrived at Jupiter and imaged its moons, planetary scientists were already starting to consider the implications that the tidal flexing might have on them. The push and pull with Jupiter might keep these worlds warmer than would be expected, for which should have frozen solid billions of years ago. Voyager 1 passed the world at a few 100,000 kilometers distant, but it was Voyager 2 that gave planetary astronomers their first close-up look at the world. They saw a moon covered in ice, without the impact craters common on every other solid world in the solar system. Something was constantly resurfacing the crust of Europa. The brown streaks across the surface looked like cracks in the ice where regions moved around like the plate tectonics here on Earth. Could there be a liquid ocean beneath this icy crust? If there's liquid water, is there life down there? The discoveries made on Europa have been made again and again across the solar system. Enceladus is the best example. NASA's Cassini spacecraft discovered huge geysers of water ice spewing out into space, and more recently, it turned up evidence that hydrogen gas is present in the water. This hydrogen is the ideal nutrient for bacteria here on Earth. So it seems even more likely that an ecosystem could be down there beneath the ice on many of these ocean worlds. Even more recently, astronomers discovered that Europa has the same geysers of water ice found on Enceladus. We're starting to see a pattern here. One big mystery about ocean worlds was recently solved. The smaller worlds like Enceladus should have frozen solid years ago, even with the tidal interactions with Saturn and the decaying radioactive material inside it. In a new study in the journal Nature, a worldwide team of researchers, including folks from NASA, have used data from Cassini to develop a model for how it could have kept liquid. It appears that Enceladus has a porous, sponge-like core, which water is squeezed through by the tidal interactions with Saturn. By constantly cycling its water through its rocky core, Enceladus keeps its oceans liquid. And maybe this mechanism is behind liquid oceans on many worlds. According to Monsavi Lingam and Abraham Loeb from the Harvard-Smithsonian Center for Astrophysics, there are hundreds and maybe thousands of times more of these worlds than the terrestrial planets we've been looking for in the habitable zones of other stars. The habitable zone is the region around a star where liquid water can be present. Too close, and water boils away. Too far, and water freezes and stops being useful to life. That's why it's the Goldilocks zone, where it's just right. But this habitable zone doesn't mean that any worlds within this zone are actually habitable. In our own solar system, Venus and Mars are within the habitable zone like Earth, but Venus had a runaway greenhouse effect, while Mars lost its atmosphere eons ago. For a world to actually be habitable, it needs to have that perfect temperature, where the water is actually a liquid on the surface. But these icy ocean worlds discovered here in our solar system already have that prerequisite for life. They're largely made of water, and they all seem to have some kind of liquid ocean surrounded by a crust of ice. Stars blow out solar winds of charged particles. There's the constant radiation coming from galactic cosmic rays. Planets like Jupiter can generate deadly magnetospheres of trapped radiation around them. But for these ice worlds, that's no problem. Radiation can't pass more than a few meters down. Again, according to Lingam and Loeb, the lack of sunlight is certainly a problem. So you're not going to get the density of a biosphere that we have here on Earth. There'll be just fewer organisms than a place like our planet. And those life forms are more likely to be simpler, single-celled bacteria than the larger, complex life forms that we have here. So maybe not European space whales. But if you're looking for raw numbers, statistically speaking, they estimate that there could be 1,000 ocean worlds for every rocky planet that exists within the habitable zone of a star. Of course, detecting these worlds is going to be difficult. You could search for hotspots on ocean worlds, but these could be volcanic hotspots. The best solution is to go and drill down through the ice to sample the water beneath. One of NASA's next flagship missions is known as Europa Clipper, scheduled to launch in the 2020s. It'll fly to Jupiter and its moons. It'll then make regular flybys past Europa, as many as 45 over the lifetime of its mission. And during this time, it'll capture close-up images and scientific data in the dangerous radiation environment of Europa, and then speed off to safety. It'll have the standard suite of cameras, mass spectrometers, and other scientific sensors, but one of the most interesting instruments will be an ice-penetrating radar that'll be able to peer several kilometers through the ice shell to figure out how thick it is, and if there are pockets of liquid water closer to the surface, places that you could drill down to try and reach. The potential for life to flourish on an ocean world has serious implications for the spread of life in the universe. And we'll get to that in a second. But first, I'd like to thank Dominic Santerre, Jeff Truman, Glenn Hall, and the rest of our 785 patrons for their generous support. If you love what we're doing, you want to get in on the action, head over to patreon.com/universetoday. If there are thousands of times more water worlds out there than terrestrial planets, that's really where the life is. And these worlds will have completely isolated biospheres, cut off from their star. In fact, a world like Europa orbiting around a planet like Jupiter wouldn't care whether there was a star at all. The tidal interactions with the planet would keep the world melted, allowing life to survive for eons. Again, in their study, Lingam and Loeb note that these kinds of worlds have thick atmospheres and subsurface oceans that could float through interstellar space and continue to support life. They calculated that if Earth was ejected from the solar system into deep space without the sun, the oceans would freeze down to a depth of 4.4 kilometers. But below that, in places like the Mariana Trench, life would go on in these subsurface lakes for eons. Earth could drift through space for millions or even billions of years until it encounters another star system and gets warmed up again. Life for us might be relatively short-lived, but life on Earth is here to stay. We think about Europa and Enceladus as the places for liquid water, but researchers think there could be liquid oceans at Pluto, Eros, Sedna, any place that has a large amount of water. Just there could be life on Pluto right now. There's so much water out there in space, and it's the ideal place to search for life elsewhere in the solar system and in the universe. Of course, because it could be locked down beneath the ice, we'll need to develop exotic new techniques and measure and observe it. And that means new missions with new technologies that can peer through the ice to find pockets of water underneath, or fly through European geysers and sample the chemicals close up. It turns out our search for life in the universe has just begun. Where do you think we should be searching for life in the universe? Do you have some clever ideas to detect life on ocean worlds? Let me know your thoughts in the comments. And do you want to know when we release a new episode? Are you worried that YouTube is going to be accidentally unsubscribing you? I've created an email mailing list to announce new videos when we post them. Here's the link, and I'll also put it into the show notes for this episode. And in our next episode, we'll talk about biosignatures. What kinds of chemicals would we need to detect in the atmosphere of an extrasolar planet to know that there's life there? It's a surprisingly tricky problem, and that's next time.